Okay. So this next and final operational property of the Laplace transform that we want to talk about deals with periodic functions. Your book will go into more depth and more examples than we're doing here. We really just kind of want to scratch the surface on this one and do one example before wrapping up section 7.4. So as a reminder, you deal with periodic functions for the first time in trigonometry when you talk about sine and cosine. But in the general sense, when you define a periodic function, this is the definition. So a function f is called periodic if there exists a positive real number t such that f of t, little t, is equal to f of t plus capital T for every value of t that you can plug in here. And if this capital T is the smallest such positive number that makes this true, we call capital T the period of that function. So for example, if f of t was equal to sine of t, then this capital T can be equal to 2 pi. Sine of t has a period of 2 pi. It can also equal 4 pi. So there's different values that will work for this capital T, but there will be a smallest number if this function is periodic, and that smallest number is called the period. So that's just a little reminder. You should already know that from previous classes. Here's where we're going to use this with the Laplace transform. So if we have a piecewise continuous function f of t, and it's piecewise continuous in the non-negative reals, and if it's of exponential order, and if it's periodic with period t, then the Laplace transform of f of t is equal to this, 1 over 1 minus e to the negative s times capital T, the period, times the integral from 0 to capital T again, of e to the negative st f of t dt. Okay, so the way that we're going to prove this, and it's a fairly short proof, is using something we've done before. We know that the Laplace transform deals with an integral from 0 to infinity, but we can split that into two integrals. So we're going to split it into an integral where the interval that we're integrating over is exactly the length of the period, 0 to t. And then the second integral takes care of everything else from t to infinity. Okay, now we're going to use a substitution. So if we set t equal to u plus capital T, the period, then dealing with just this last integral right here, starting with the limits of integration, remember this the variable here is t, so I'd plug capital T in for this t right here. Subtracting t from both sides would say that 0 is equal to u, so my lower limit of integration becomes 0. The upper limit of integration will still be infinity, and it should be fairly easy to see why that happens. T, this lowercase t here, will become u plus capital T, and this t right here will become u plus capital T. And so our second integral has turned into this guy right here. Okay, now I can take the negative s and distribute it in. Oh, my dt became du. I wanted to point that out also. The negative s times that capital T right there would be considered a constant in this integral. So e to the negative s capital T can be brought out of the integral like this. Okay. In addition to that, the function f is periodic, and t is its period. So according to the definition of period, f of u plus t should be equal to f of u. Again, we're using this definition right here. Okay, so that means this entire integral simplifies down to this. But the integral that remains out here resembles a Laplace transform. So this thing is equal to e to the negative st, which we're seeing here, times the Laplace transform of f. And the variable u can be relabeled as a t again. It's fine to do that. Okay, so now using what we have here, we evaluated the second of these two integrals, so I could take this and put it here. And notice I'll have a Laplace transform of f of t showing up on this side and another one showing up on this side. So I can solve for the Laplace transform of f of t. And I'll let you do the algebra, but the algebra for that, we would end up with this right here. And the end result would come from simplifying what we see here. Okay, so I would subtract this term over here, factor out the Laplace transform of f of t, divide by what remains. You're going to end up with this result. right here. Okay, so I'll let you kind of fill in the gaps getting from here to here. It's just a couple of algebraic steps. So the way I want to wrap this up is doing an example where we're finding the Laplace transform of a function that's periodic, and all we have to go on is its graph. Okay, you have a couple of homework problems that deal with this. So here's a graph. We can see it's we're told that it's periodic, and we can kind of see that in the graph, and it looks like it's alternating between 1 and 0. So it's kind of like, it's similar to that Heaviside function or that unit step function that we talked about in the previous section. I would like to come up with a piecewise function that is described, or that this graph is describing. F of t is equal to 1 when t is between 0 and a. I can see that from the graph. So 0, a. And then it becomes 0 on the interval from a to 2a. And then after that, it just repeats. 1, 0, 1, 0, 1, 0. So it's clear that the period of this thing is 2a. That's how far we have to go before we start seeing the repetitive pattern. So I'm going to say that f of t equals f of t plus 2a for all t. That's indicating that this is the period. Okay, so 2a is going to fill the role of the capital T in our theorem up here. Now I can use my theorem. So f of t, the Laplace transform of f of t is equal to what? Okay, we're going to use this formula right here. It's equal to 1 over 1 minus e to the negative st, where t is actually 2a. So I'm going to write that this way, negative 2as, times the integral from 0 to capital T, which again, remember that's 2a in this case, of e to the negative st, times my function f of t dt. Now, in order to go further, I'm going to have to use my piecewise definition for this function. So this is equal to 1 over 1 minus e to the negative 2as. And if you remember, when you want to find the integral of a piecewise function, we split it up into a sum of integrals where we use each piece of this function as an integrand once. So for example, on the interval from 0 to a, I'm using the function 1 for f of t. That means I would be looking at the integral from 0 to a of e to the negative st times 1 dt, plus the integral from a to 2a, now I'm using the second part of this function, of e to the negative st times 0 dt. Okay? Clearly, this integrand will be 0, which means the whole integral goes to 0. So this is equal to 1 over 1 minus e to the negative 2as times the integral of e to the negative st. And I can integrate that pretty easily. That would be equal to, we're integrating with respect to t here, so that would be equal to negative e to the negative st over s from 0 to a. Finally, evaluating that, I get 1 over 1 minus e to the negative 2as times, plugging in a for t first, I get negative e to the negative as over s minus negative, so it'll be plus. Plugging in 0 would give me a 1 here, 1 over s. And I could try and combine things and simplify things. I'm not going to worry about that here because this is going to be fine for an answer. Okay, that's literally all we're going to be doing with this last property. Again, I said it already, the book will go into more depth with this property, but we don't need those results for what we're doing in this class. So we're going to be stopping 7.4 here.